Okay, hi, linear algebra. So I'm picking up where we left off on, I think it was the second page of notes where we were talking about the fact that the functions that you are testing closure over don't always have to make sense in quotes. Okay, and so I just left my second section, so my large section, and of course I did this with only 30 seconds left, which was very disturbing. And what I told them was, and this is the truth, addition as you know it is not all that addition is. Now, if you're going to want to say this more dramatically, what you can just say is, oh my gosh, mom, I just learned that addition really isn't addition, which is a much more provocative thing to say. And I know that you all as young people like to have really catchy, dramatic things to say because therefore rumors spread more wildly. So you can go ahead and say, I just learned that addition really is an addition. And while that's a very catchy thing to say, what's really more accurate is the fact that addition, at least as you have known it, is not all that addition is, okay? And that is true. So this is where when Nick asked me this in class, he said, why do I even call this the addition function if what you're doing is multiplying? I said to him, oh, I just realized I skipped over a whole discussion. And the discussion is one that should make you feel hopefully incredibly uncomfortable, mildly sick. And it's a good thing because what's happening here is your world is being turned upside down. The bottom line is addition is whatever you want it to be. Okay, the addition function in the context of testing closure of a set is whatever you want to define it as. Now, who was it? Kat asked, why do I have to call it the addition function? Why can't I call it like the lima bean function or the whatever function or the watermelon function? And what I said to her, I said, well, we have to call it the addition function and we have to call it the scalar multiplication function because what we're going to learn in about a day is that sets that are closed under these two functions, specifically addition and scalar multiplication, have unique properties. Now, without giving too much away, sets that are closed under these two functions are called vector spaces. And once you know that a set is a vector space, there are certain things you can then do with them, okay? But, and this is where people were getting very upset at me, which is fine because that's where you should be. If the addition function though really isn't the addition function, aren't we being disingenuous? And that's when I dropped the bomb of the day, which is, well, but the truth of the matter is addition as you've known it is just what is referred to as standard conventional addition. It's like addition JV, all right? There are varsity and prep levels of addition that are not merely what we think of addition to be. And with that, I hope that I have made you very uncomfortable. And if I have done that, then I have succeeded. But for now, and again, if you want, here's the thing too, I think it's really important. If you want to kind of make this newsworthy, AKA like SSA newsworthy, I think we should maybe contact George Gruen, who I think is a very funny human being, and we should make this part of the next newscast because this is news. And what will be really lovely is it will throw all of the underclassmen into a state of complete and utter panic. And I, for one, would love to see what that looks like. But I digress. So with that, hopefully you're uncomfortable, which is great. Let's see, though, let's test whether this set is closed under addition. Now, under this addition function. So we're going to see, is it true? Okay, so let's take a look. If A and B are real numbers, let's see if we can work this through. Well, is it true that the product of two real numbers is going to be a real number? And we talked about this today, I think. We said that this is, in fact, an element of the real numbers because any real times any real has to equal a real. And in fact, the only way that a real number times something could result in an unreal number or an imaginary number is if this number right here was non-real or imaginary. And since A and B both have to be real, we know that the addition function, which is defined as a product, is yielding an element that is still the set of real numbers. So therefore, S is closed under addition. Okay? Yes, I know you're very disturbed when you write the word addition because you're saying, well, I wrote addition. Well, actually, I should write this under the addition function. And the addition function was given to you, right? All right, let's test scalar multiplication function. And we're checking closure under the scalar multiplication function. By definition, this scalar k can be any scalar. It doesn't have to be integral. We do say that k has to be a real number, okay? So that's unwritten but understood. When you talk about scalar multiplication, it has to be any real number. Well, let's talk about it. Let's see. K times a, so any scalar times a is going to be that real number raised to the power of k, right? And if we think about this, a raised to a power of k is going to be a times itself k times. Now, a times itself k times, I want you to not be so literal. That doesn't mean that I'm assuming that k is integral, right? Like I know, for example, if k is 1/2, so, okay, if k equaled 1/2, I'm fully aware that k times a would then equal root a, all right? But I'm just being loose here. The fact of the matter is that if you have a real number raised to some power, whether that power k is non-integral, whether that power k is equal to 0, whether that power of k is negative, right? So this here would be like the 10th root of a cubed, for example, all right? The point here is that if a is a real number and k is any real number, a to the k is always going to equal a real number, right? For reasons that are related to the above, because the only time that a can be multiplied, and I'm using multiplied here loosely, right? Because a to the k is like a times itself k times. And I recognize that there are some exceptions, but the idea is the same. The only time a times something is going to give you a number that's not real is if that number, the second number that you're multiplying a by, is imaginary. So the point here is that k times a, which equals a to the k, will always yield a real number. So once again, S is closed under the scalar multiplication function. Okay, I know this is so difficult for you. I understand. It's okay. It's good for you. All right. Okay, now let's do this. Sometimes you'll see a question like this. Write it down for me. I'm going to say S equals the set of all polynomials. Now let's just have a little refresher. Polynomials. The polynomials have terms where the base is the variable and the power of the base, or the x, can only be integral and non-negative. So polynomials could look like this. Okay, polynomials cannot look like this. Polynomials cannot look like this. Okay, so polynomials have to have integral degrees of all terms, integral non-negative degrees of all terms, and the constant is often referred to as the constant or the coefficient of the degree 0 term. S is the set of all polynomials. Now, here is when you're asked to test, when you're asked to test or determine closure or not closure, okay, over the following functions. Okay, when you're asked to test closure over a function that is just addition as you've known it for the past 18 years, you'll have something written like this: standard conventional addition function. Okay, and then it also say test over the standard conventional scalar multiplication. So here is new vocabulary for us. From now until the end of time, when you're asked to add something, you can say, Barney, do you mean standard conventional adding, or do you mean some alternative addition function you want to tell me the answer to, or give me the description of? Standard conventional addition or standard conventional scalar multiplication is what we'll call just regular old addition or simple addition, or the addition you learned in kindergarten. So let's see, let's test the set of all polynomials, where S is the set of all polynomials. Is the set of polynomials closed under standard conventional addition? The answer is it is, because if you add two polynomials, when you add two polynomials, the result is always going to be a polynomial. There's no way you can add two polynomials and get terms that have, for example, negative degree or roots, right? If you're adding two polynomials, you will only have non-negative integral terms. So this set is closed under under standard conventional addition. This set is also closed under standard conventional scalar multiplication, because if you multiply any polynomial by a scalar, and that scalar could be integral or not integral, the only thing that's going to change of the polynomial is just the coefficients. And a polynomial can have non-integral coefficients. For example, I mean, this is just as much a polynomial as the one above. What makes a polynomial is the fact that the powers of the variable x have to be non-negative integers. So in this case, this set is indeed closed under these two standard conventional operations. Okay? Now with that, what I'd like you to do is to then look at your homework. Actually, lucky you, I can't exactly assign homework yet, because we need one additional idea, and the idea of what a vector space is, I want to wait until we're together to go over. But hopefully, if you've listened to the screencast and been disturbed, and you go away with this by saying, I want to tell the world that addition is not addition, consider your homework done, okay? I will see you either tomorrow or Wednesday, assuming there's no sudden frost or snow. Goodbye.